In this episode, we focus on a shift in thinking that separates fragile software from trustworthy software. Software assurance should be built into engineering decisions from the start, not treated as a last-minute testing checklist. Many beginners imagine security as something you bolt on after an application is written, like painting a house after it is built. But security problems are often created much earlier, when teams choose designs, define data flows, and make assumptions about who will use the system and how. Software assurance is the confidence that the software does what it is supposed to do, does not do what it is not supposed to do, and behaves predictably even when someone tries to misuse it. That confidence comes from choices about requirements, architecture, interfaces, and error handling, not just from running tests at the end. Testing is important, but if the underlying design encourages risky behavior, testing can only find so much, and it often finds issues when they are expensive to fix. By the end, you should understand what software assurance means at a beginner level, why early decisions matter so much, and how assurance can become a normal part of building software rather than a stressful end-of-project scramble. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To make this concrete, start with the idea that software is a set of decisions made visible. Every button, field, and background process reflects choices about what data to accept, what actions to allow, and what errors to tolerate. When those decisions are made without a security mindset, software tends to be permissive and trusting, which feels convenient during development but becomes dangerous when the software meets the real world. Attackers look for places where software trusts inputs, trusts identities, or trusts internal messages without verifying them. They also look for inconsistent behavior, because inconsistency often signals that developers made assumptions that do not hold in all cases. Software assurance is about turning those assumptions into explicit, defensible rules that are implemented consistently. This means assurance is less about catching bugs randomly and more about intentionally shaping software behavior so that the safe path is normal and the unsafe path is blocked or contained. If you think of software as a set of promises, assurance is what makes those promises believable. A major reason checklists are not enough is that they often focus on symptoms rather than causes. A checklist might remind a developer to sanitize inputs or to avoid hard-coded secrets, but it may not address deeper decisions like whether the system needs to accept that input at all, whether the feature should exist, or whether the data should be stored in a way that reduces harm if exposed. If the system design requires large amounts of sensitive data to be handled everywhere, then even careful input handling will not eliminate the risk created by widespread data exposure. If the architecture mixes high-risk administrative functions into the same exposed interface used by ordinary users, a checklist item about authentication may not prevent a single vulnerability from becoming catastrophic. Assurance built into decisions means you ask early, what is the minimum data and capability needed to meet the mission, and how can the design limit harm when something fails? That is not a checkbox, it is a set of engineering choices. Those choices determine whether later testing is a final verification step or an endless hunt for surprises. Requirements are the first place software assurance begins, because requirements define what the software must do and, just as importantly, what it must not do. Beginners often focus on features, like being able to submit a form or generate a report, but assurance-minded requirements also include constraints, like who can access a report, how long data should be retained, and what should happen when something is missing or invalid. Good security requirements are specific enough to guide design decisions and to be validated later, but not so vague that everyone interprets them differently. For example, a requirement that says data must be protected is not very helpful, while a requirement that says only authorized users may access their own records and that bulk export must require special authorization gives designers something concrete to implement. When requirements are clear, developers can make consistent choices and testers can verify behavior meaningfully. When requirements are unclear, security becomes a debate at the end, and debates at the end tend to become compromises that favor speed over safety. Architecture decisions are another major assurance foundation, because architecture controls where trust boundaries exist and how responsibilities are separated. If an application is designed as one large component with many responsibilities, then small mistakes can have large consequences, and assurance becomes difficult because the system is hard to reason about. If the design separates responsibilities, such as separating user-facing functions from administrative functions and separating data handling components from presentation components, you create natural containment. That containment supports assurance because it limits where sensitive operations can occur and limits which parts of the system can reach sensitive data. Architectural decisions also include how the system handles identity, how it manages sessions, and how it enforces authorization, and these are not details you want to decide at the last minute. When identity and authorization are treated as consistent architectural concerns, they can be implemented uniformly and reviewed effectively. When they are treated as scattered implementation details, you often get inconsistent checks and accidental bypass paths. Another assurance-building decision area is data flow, which is about how information enters, moves through, and leaves the system. Data flow thinking helps you see where validation must occur, where transformations happen, and where sensitive data might be exposed unintentionally. Beginners sometimes assume that once a user is authenticated, their inputs are trustworthy, but authenticated users can still make mistakes and can still be attackers. Assurance-minded design treats every input as potentially harmful until validated, regardless of who sends it. It also treats internal messages between components as potentially untrusted unless the system has a way to verify they are legitimate and unchanged. When data flow is understood early, you can design proper validation points and avoid unnecessary duplication of sensitive data across many components. If you do not understand data flows until late, you often discover that sensitive data is spread everywhere, and cleaning it up becomes complex and expensive. Good assurance reduces data exposure by design, making later controls easier to apply consistently. Error handling and failure behavior are also surprisingly important for software assurance, because many security issues are really failure issues. When a system fails, it might reveal sensitive details, allow an action to proceed without proper checks, or behave unpredictably in ways attackers can exploit. A common example is when an error message reveals too much about internal logic, but a deeper example is when an error causes a security check to be skipped. Assurance-minded engineering decides early how failures should be handled, such as failing closed when security-relevant information is missing, meaning the system denies the action rather than guessing. It also means being consistent about how errors are reported, logged, and recovered from, so that defenders can understand what happened without leaking details to an attacker. Predictable failure behavior is a form of safety because unpredictable systems are easier to exploit and harder to defend. When teams build failure behavior into design decisions, they reduce the chance that rare edge cases become the attacker's favorite entry point. Software assurance also depends on supply chain choices, which includes the libraries, frameworks, and components a project relies on. Beginners might assume that using widely known libraries automatically makes a project safe, but every dependency is part of your system's behavior, and therefore part of what you must assure. Assurance-minded engineering includes deciding which dependencies are appropriate, understanding what they do, and avoiding unnecessary dependencies that expand the attack surface. It also means planning for updates and changes, because dependencies evolve over time, and what was safe last year might not be safe today. This planning is not about chasing every update in panic, but about designing processes that make updates manageable and visible. When dependency decisions are left until the end, teams often take shortcuts, adding libraries quickly without considering long-term risk. Building assurance into engineering decisions means you treat dependencies as intentional parts of your system, not as random add-ons. Testing still matters, but its role changes when assurance is built into decisions. Instead of testing being the first time you think seriously about security, testing becomes a way to verify that the security intentions of the design are actually enforced. In that world, tests can be aligned with requirements and architecture, and they can focus on the most important properties, like authorization correctness, input validation consistency, and safe failure behavior. Tests can also help prevent regression, meaning that when changes are made later, the system does not silently lose its security properties. But if the design is weak, tests become a game of whack-a-mole, catching one bug while missing deeper systemic issues. That is why the phrase "not just testing checklists" is important. Checklists can be useful reminders, but they cannot replace intentional design. Assurance is strongest when the system is designed so that insecure states are difficult to create in the first place. Another important part of assurance is making security decisions visible and reviewable, because hidden decisions are hard to validate. When a system has clear rules about access and data handling, those rules can be reviewed, reasoned about, and tested. When security decisions are implied through scattered bits of logic, assurance becomes guesswork. Review does not have to mean formal ceremonies. It can mean that the system is built in a way that encourages shared understanding. For example, consistent patterns for authorization checks and consistent handling of sensitive data make it easier for peers to notice when something deviates from the norm. This supports a culture where developers can catch security issues early without needing to be security experts. Assurance improves when good patterns are easy to follow and bad patterns stand out. This is an engineering design outcome, not a policing outcome. A final misconception to address is that software assurance is only about preventing attackers. It is also about building software that behaves reliably, protects users from mistakes, and supports recovery when something goes wrong. A system that can be understood, monitored, and repaired is a system that can be defended, because defenders need visibility and control. Assurance-minded decisions include making logs meaningful, making state changes traceable, and making recovery procedures feasible without heroic effort. These choices reduce the chance that a small issue becomes a major incident, because teams can see problems earlier and respond more confidently. They also reduce the temptation to create risky workarounds, because the system supports safe operation even under pressure. In that sense, software assurance is about operational trust as much as it is about technical correctness. As you conclude this lesson, the central message is that software assurance is not a final inspection. It is a design philosophy that starts with requirements and continues through architecture, data flows, error handling, dependency selection, and reviewable patterns. Testing and checklists remain valuable, but they are most effective when they confirm a well-designed security story rather than trying to invent one at the end. When assurance is built into engineering decisions, the software becomes easier to reason about, easier to maintain, and harder to misuse, which reduces the number of surprises that turn into incidents. When assurance is treated as a checklist at the finish line, teams often discover late that the design created unnecessary risk, and they are forced into rushed fixes that may not hold up. For a beginner, the best habit to build is to ask early, what could go wrong? What is the impact? And how can we design the system so that wrong things are difficult to do and easy to detect? That habit turns software security from a frantic afterthought into a stable engineering practice that supports trust over the entire life of the system.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.